Ever wonder how your phone can understand what you're saying or how your computer plays music? Well, it all comes down to the hidden language of our digital world, discrete time signals and systems. It sounds complicated, but it's the secret sauce behind so much of our tech. So let's dive in.
Our world is just filled with signals. The sound of a guitar, the light from the sun, they all exist as what we call analog signals. Just think of a smooth, continuous wave flowing through time. It's kind of the natural language of the universe.
But here's the thing. Your laptop, your phone, they don't get waves. They don't speak analog. They speak in numbers, pure and simple. So the big question is, how do we bridge that gap? How do we translate our world into a language that these powerful machines can actually work with?
And that brings us to our first big step, from waves to numbers. This is all about that translation process, taking that smooth, natural wave and turning it into a list of numbers that a computer can finally read. So if we want to get a little mathematical about it, we describe that sound wave with a function x of t. That t just stands for time, and the key thing here is that it's continuous. The signal exists at every single moment, every fraction of a second. So to get that wave into a computer, we have to do something called sampling. It's a really crucial step. Think of it like taking a series of snapshots of the wave at perfectly regular intervals. Instead of trying to capture the whole infinite wave, we're just grabbing a set of measurements that represent it. And boom, this is what you get. That smooth wave, x of t, has been transformed into a discrete time signal, x of n. It's not a continuous line anymore. Now it's just a sequence of individual values, a list of numbers, and that is something a computer can finally get to work on.
Okay, so now we get to signals, a sequence of information. We've got our signal as a list of numbers, so what can we actually do with it? Well, it turns out you can do some really powerful things with some surprisingly simple math.
And this is the really cool part. Because it's all just numbers now, we can treat them like numbers. We can add two signals together, we can make a signal louder or softer by scaling it, or we can multiply signals. These basic operations are the fundamental Lego bricks for everything else we're going to do.
So we have our signals, our sequences of numbers, but what does the actual processing? Well, that's where this next section comes in. Systems, the signal processors. You can think of a system as the engine that does all the heavy lifting.
At its heart, a discrete time system is really just a recipe. It's a set of rules, a mathematical operation that takes in one sequence of numbers, our input signal, and spits out a new, transformed sequence of numbers as the output. It's like a black box for signals.
Let's make this real with a classic example, an echo. What is an echo? It's just the original sound, right? Plus a slightly quieter version of that same sound that you hear a moment later. A system can do that. It just takes the original signal, makes a delayed, quieter copy, and adds them together.
And here's what that recipe looks like as an equation. The output, y of n, is just the original input, x of n, plus a version of that input that's been delayed by d and made quieter by alpha. See, it's just simple addition and multiplication, but it creates a totally new audio effect.
Now this is where things get really elegant. Let's talk about the system's unique fingerprint. So if you have one of these systems, how do you figure out everything it's capable of? Do you have to test it with millions of different signals? Well, it turns out you only need one. And that one special test signal is called the unit impulse. It is literally the simplest signal you can imagine. It's just zeros, everywhere, except for a single value of 1 at one point in time. Think of it like this, a completely silent room, and then one single sharp clap. That's it. That's our ultimate test. So the whole game is about what happens when you feed that one single clap, that unit impulse, into your system. The output you get, the sound that comes out the other side, that's called the system's impulse response. It's the system's unique reaction to that one tiny input.
And this is the mind-blowing part. That impulse response is everything. It's like the system's unique fingerprint, its DNA. It tells you absolutely everything about how that system will behave. If you know the impulse response, you can predict what the system will do to any signal you throw at it. It's the master key.
Okay, let's bring it all home with our final section, the power of digital processing. We've gone from waves to numbers, and we've seen how these systems use math recipes to change them. So what? Why does this matter? Well, because this simple framework is the engine behind pretty much all of modern technology. I mean, the applications are literally everywhere. Speech recognition on your phone, making your photos look better, the digital audio in your music and movies, secure communications. All of these incredibly complex technologies are built on these exact same fundamental ideas of sampling signals and processing them with systems.
So, I'll leave you with a final thought. We saw how a simple recipe, a simple system, could add an echo to a sound. But what if you wrote the recipe to do the exact opposite? What if you designed a system specifically to find an echo in a recording and remove it?
And right there, that is the essence of digital signal processing. It's the art of turning our world into numbers and then designing these clever mathematical recipes to enhance, to fix, and to completely transform that information in ways that honestly feel a little bit like magic.